Welcome to the Thinking Abyss podcast, a philosophical journey through consciousness, reality, and the phenomena that challenge our understanding of existence. From ancient wisdom to cutting-edge theories, we explore where philosophy meets science and curiosity leads to the edge of the unknown.
I want you to try a little experiment with me. It's a visualization exercise, so if you're driving, please keep your eyes on the road, but, use your mind's eye.
Okay, I'm game.
Picture a sprawling green park. It's a sunny Saturday afternoon.
Sounds pleasant. I'm picturing it now.
Okay, now I want you to focus on a dog running across the grass. Let's make it a golden retriever.
A classic.
Yeah, classic. Ears flapping, tongue lolling out, chasing a tennis ball. Just pure energy. You got it.
I have the dog. It's a very happy dog.
Now, in that same park, picture the jagged gray rock that the dog just clumsily tripped over. It's half buried in the dirt. Maybe it's got a bit of moss on it, and it's completely still.
Okay. Dog and rock. Got them both.
Now answer me this. In your gut, in your absolute deepest intuition, you know the difference between those two things.
Of course. It's night and day.
The dog is alive. The rock is not. It is, I think, the most intuitive, obvious distinction in the human experience.
Mm-hmm. A toddler gets it.
A toddler gets it. You don't need a PhD in biology to tell them apart.
Yeah.
We have this built-in binary switch in our brains.
Yeah.
Animate versus inanimate.
Subject versus object.
Living versus dead. Exactly.
It is the fundamental categorization of the human mind. We organize the entire universe into those two buckets before we even learn to speak.
Exactly. And that is why today's investigation is going to be so incredibly frustrating and hopefully completely mind-altering. Because we have a stack of research here. Articles, essays, some really heavy scientific breakdowns that argue that our gut instinct is wrong.
Or at least it's an illusion, a very convincing one, but an illusion nonetheless.
Right. The sources argue that when scientists actually try to draw a sharp scientific line between that dog and that rock.
When they try to pin it down.
Yeah, when they try to write down a definition that rigidly includes every living thing and excludes every non-living thing, the whole concept just falls apart.
It doesn't just fall apart, it evaporates. The closer you look with the tools of physics and chemistry, the more you realize that the border between biology and physics doesn't actually exist.
Not in the material world.
No, it's a line we draw in our heads, not a line drawn in nature.
And that is our mission today. We are going to deconstruct the definitions of life that we all learned in school, expose their flaws, and see if we can rebuild a new understanding. We're going to find out that life isn't some magical spark. It's not a special ingredient. It's just physics doing something incredibly weird.
I'd say physics behaving elegantly. But yes, the goal is to stop seeing life as a noun, as a thing you have or don't have, and start seeing it as a verb.
A verb.
As a process, as a specific type of behavior that matter engages in under certain conditions.
Life is a verb. I really like that. But before we get to the high concept philosophy and all the physics, we have to start where most of us started.
Oh, yes.
9th grade biology class. I remember this so vividly. It's like chapter 1 of the textbook. The checklist of life.
Ah, yes. The characteristics approach. It's the standard pedagogy. If you want to be in the club of the living, you have to tick all the boxes.
It's so bureaucratic.
It is. It's a very bureaucratic way of defining existence.
It is. It feels very safe and neat. So let's run through this list from our notes, but I want to stress test it. I want to see if it actually holds up to any real scrutiny.
Let's do it. What's the first requirement on that list?
Metabolism. That's the big one. To be alive, you have to consume energy, you eat food, you breathe air, you break it all down, and you use that energy to do stuff.
That seems fair. You need a throughput of energy to maintain your structure. If you stop eating, eventually you reach equilibrium with the environment.
Which is a very fancy way of saying you die.
A very fancy way of saying you die, yes.
Okay, second on the list, growth and reproduction. You start small, you get bigger, and eventually you make a copy of yourself. You pass on your genes to the next generation.
The perpetuation of the pattern. That makes sense. Without reproduction, life ends in one generation. So that seems pretty essential.
Third, response to environment. If I poke you, you flinch. If the sun comes out, a sunflower turns toward it.
Stimulus and response.
Yeah, if a bacterium senses sugar, it swims toward it. You have to be able to sense the world and react to it.
It implies some level of agency or, at the very least, sensing.
Okay. Fourth, homeostasis. This is the fancy word for keeping your insides stable.
Right.
It's 30 degrees outside, but my body works incredibly hard to stay at 98.6 degrees. I regulate my pH, my water balance.
Yeah.
I am a little fortress against the chaos outside.
Correct. You're maintaining an internal steady state despite all the external fluctuations.
And finally, organization and adaptation. I'm not just a soup of chemicals. I'm made of cells, which make tissues, which make organs.
There's a clear structure.
A structure, yes.
Yeah.
And I fit my environment. So that's the list. Metabolism, reproduction, response, homeostasis, organization. And when I look at the dog, it ticks every single box. And when I look at the rock, it ticks none of them. Case closed. Why are we having this discussion?
Because you're cherry-picking the easy examples. The checklist works great for dog versus rock.
Sure.
But science isn't about what works in the easy cases. It's about what works in the edge cases.
Yeah.
And when you apply that checklist rigorously to the rest of the universe, it starts to give you some really absurd answers.
Absurd how? Give me a false positive. Something that ticks the boxes but is, definitely not alive.
Okay, let's look at a wildfire.
A fire, okay.
A forest fire.
A massive forest fire. Let's run it against your checklist. Does it have a metabolism?
Well, strictly speaking, it consumes fuel, it eats wood and oxygen, it releases energy as heat and light, and it leaves behind waste products like ash and smoke.
That is, by physical definition, a metabolic process. It's converting stored chemical energy into work and heat.
Okay.
Okay. Next, does a fire grow?
Terrifyingly so. A spark becomes an inferno. So, yes.
Does it reproduce?
It spreads. It throws off sparks, right? Little offspring that land somewhere else and start new fires.
And those new fires then grow and spread themselves. Okay, that's a check. What about responding to its environment?
Well, what happens if the wind changes?
The fire changes direction. If it runs out of fuel in one spot, it dies down. If you dump water on it, it recoils and hisses.
So it's definitely responding to stimuli. And does it have organization?
I wouldn't have thought so, but...
A flame has a specific structure, doesn't it? The hottest part is blue. The cooler part is yellow.
It has a structure. And it organizes air currents around it to feed itself oxygen. It creates its own weather system.
So according to the checklist, a wildfire is alive.
According to a strict, literal reading of the checklist, yes. Fire is doing a phenomenal impression of a living organism. It eats, grows, reproduces, and responds.
But we know it's not alive. It's just a runaway chemical reaction. It has no cells, no DNA, no evolution.
Exactly. So the checklist has failed its first test.
Okay, so fire is the trickster of the non-living world. It cheats the test. But surely that's just one weird anomaly.
Not really. Take a simple salt crystal.
A crystal. Yep. If you put a small crystal in a saturated saltwater solution, what happens?
It grows. It gets bigger.
It grows, and it organizes chaotic, randomly floating molecules into a perfect geometric lattice. That's extreme organization, far more ordered than a living cell.
Okay.
And if you break that crystal in half, you now have 2 seed crystals, and they will both continue to grow.
So it has reproduced.
In a way, yes.
But it's a rock. It's a fancy organized rock, but it's a rock.
Exactly. But it ticks the boxes for growth, reproduction, and organization. And let's bring it into the modern world. Look at your laptop or the server that's hosting this audio.
My laptop is definitely not alive. It crashes way too often to be intelligent.
But look at the list again. Does it respond to stimuli?
Well, yes. I press a key, a letter appears, I click the mouse, window opens. That's a response.
And does it maintain homeostasis?
Actually, yeah, the fans. When the processor works hard and gets hot, the fans spin up to cool it down. It regulates its internal temperature to keep operating.
And it consumes energy electricity to do work, just like metabolism. So we have machines and chemical reactions taking off 50–60% of the life test. The line is getting really blurry.
Okay, I see the problem with the false positives. But what about the other way around? Are there things we know are alive that actually failed the test? Because if there are, the definition is completely useless.
Absolutely. And this is where the biological definition gets really cruel. Let's talk about the mule.
The animal, the offspring of a donkey and a horse.
Right. And mules are famously biologically sterile. They have an odd number of chromosomes. They cannot reproduce.
Okay. Oh, I see where this is going.
If reproduction is a mandatory box on the checklist, if it is a requirement for life, then a mule is not alive.
That's just ridiculous. It's walking, eating, breathing, thinking. It is clearly, obviously alive.
Or think about humans, a postmenopausal woman, a man who is infertile, or even a child who hasn't hit puberty yet.
They can't reproduce.
They cannot reproduce. So are they dead, according to biology?
Of course not. That would be an insane definition.
So we have to throw out reproduction as a hard and fast rule. It's a usually, not an always.
This is starting to feel less like science and more like a a suggestion box, things that are often alive. And we haven't even touched the biggest controversy in biology yet. The viruses.
The ultimate headache. The
Yeah.
grayest of the gray areas.
I've always heard conflicting things about viruses. I mean, what is the final verdict? Are they alive or not?
If you use the checklist, they are a complete mess. Viruses have genes, they have DNA or RNA, a blueprint,
Right.
and they evolve. We see that every single flu season.
Yeah.
They adapt to our vaccines, so they have organization and adaptation.
But
They have no metabolism, none whatsoever. They are cold, they don't eat, they don't breathe, they don't produce weight.
they're floating code.
They are basically a USB stick with a blueprint on it wrapped in a protein shell. If you leave a virus on a table, it just sits there like a grain of salt. It does nothing.
It only activates when it gets inside a host cell.
Exactly. It has to hack into a cell and hijack that cell's machinery to make copies of itself.
So they fail metabolism and they fail independent reproduction.
Correct.
But they cause pandemics. They can wipe out civilizations. It feels incredibly arrogant to just call them inanimate objects or dead matter.
And that's why most biologists just punt. They categorize them as obligate parasites or at the edge of life.
At the edge.
But the fact that we have to use phrases like at the edge proves the point. The checklist fails because it tries to force a binary choice, alive or dead, onto a universe that doesn't work in binaries.
So if the checklist is broken, what do we replace it with? If I can't look at the traits, the characteristics, what do I look at?
You have to stop looking at the biology and start looking at the physics. You have to look under the hood.
The source material we're looking at has this great quote: biology is just chemistry, and chemistry is just physics.
That is the fundamental truth of it. We have to purge this idea of vitalism from our heads.
Vitalism, that's the old Victorian idea, right? That living things had some kind of spark, a soul, a mystic energy that made the muscles move.
Right, like Dr. Frankenstein using lightning to animate the dead tissue. We used to think there was a special life force, or élan vital, that defied the laws of physics.
And we know now that's completely false.
100% false. There is no spark. The carbon atom in your eyelash is identical to the carbon atom in a lump of coal. The hydrogen in your blood is the same hydrogen floating in the sun. You are made of dead stuff.
Which is a lovely thought. I am made of dead stuff.
It's true. You are a collection of inanimate particles that, when arranged in a very specific way, start behaving strangely. So the question isn't, what magical ingredient do we add? The question is, what are the physics of that arrangement?
And this brings us to what might be the most intimidating law in all of physics, the second law of thermodynamics, entropy.
The grim reaper of the universe.
Let's try to break this down for the listener who, like me, maybe hasn't taken a physics class in 20 years. What is entropy, really?
In the simplest terms, entropy is a measure of disorder or randomness. It's the tendency of things to fall apart, to spread out, to become messy.
Yeah.
If you clean your room and then you just leave it alone for a month, does it spontaneously get cleaner?
Never, not once. It gets dusty, things get moved, it degrades.
Exactly. Or if you put a hot cup of coffee on the table, does it spontaneously get hotter?
No, it cools down. It reaches room temperature.
That is the second law in action. In any isolated system, energy spreads out. Order turns into disorder. Structures crumble. The universe drives relentlessly toward equilibrium, which is a boring, uniform, lukewarm soup where nothing ever happens again.
Yeah, it's oddly depressing. But here's the paradox. I am not a soup. You are not a soup.
Not yet.
Not yet. We are highly organized. My heart is pumping. My brain is firing. I have an incredibly complex, structured machine.
Yay.
If the universe wants to destroy order, why do I exist?
You are a statistical improbability, a massive one. If I took all your atoms and put them in a giant blender for 1 billion years, they would never accidentally reform into you. You are resisting the drift toward chaos.
So is life cheating? Are we breaking the laws of physics?
This was a genuine puzzle for physicists for a long time. Erwin Schrödinger, the quantum physicist, actually wrote a famous book called What is Life back in the 40s about this very problem. He realized that life seems to violate the second law, but there's a loophole.
I love a good loophole.
The second law says entropy always increases in an isolated system. That's a system completely cut off from the rest of the world.
Like a sealed box.
A perfect thermos, yeah. But you, my friend, are not isolated. You are what we call an open system.
Because I eat.
Because you eat, you breathe, you radiate heat into the room. This is the trade-off. To keep your internal house clean, to maintain that high level of order inside your body, you have to generate a massive amount of disorder outside your body.
So I'm exporting the mess.
Precisely. You take in high-quality, organized energy food, chemical bonds, oxygen. You process it to build and maintain your structure. And then you dump out low-quality, disorganized energy heat, carbon dioxide, waste products.
So I'm paying for my life by making the rest of the universe messier.
You are. We all are. In fact, some physicists argue that life is actually better at increasing the universe's total entropy than dead matter is. We are agents of chaos, in a way. We break down energy sources much faster than a rock ever could.
The source used this beautiful analogy of the river. I want to dwell on that for a second because it really made this click for me.
The river analogy is perfect for this. Imagine a fast-flowing river. The water is rushing downhill. That's the flow of energy. That's entropy happening.
Okay.
Now imagine a rock in the middle of the river. Behind that rock, you see a little whirlpool, an eddy.
Right. A little spiral of water that seems to just stay in one place, even though the water is rushing past it.
Exactly. Now look at that whirlpool. It has a structure. It has a shape. It looks like an object. But is it a thing? Or is it just water flowing in a specific pattern?
It's the pattern. It's not a solid object. If you stop the flow of water, the whirlpool vanishes instantly.
That is what you are. You are a whirlpool in the river of universal energy. You are a stable pattern of flux.
A pattern of flux.
Matter and energy flow through you. You replace almost all your atoms every few years, but the pattern persists. You exist not by resisting the flow, but by channeling it, by going with it.
That's profound.
Yeah.
It completely shifts the whole perspective. We usually think of life as a struggle against nature, man versus the elements. But you're saying life is a result of the elements. We are just a shape that the energy takes as it falls from a high state to a low state.
We are surfing the wave of chaos. We maintain our form by ensuring the flow continues through us. We are conduits for entropy.
So if this is just physics, if organizing is just something energy does when it flows, then we should see this happening in non-living things too, right? We should see fake life or proto-life elsewhere in the universe.
And we do, all over the place. This is the concept of self-organization. The universe loves to build structures, even without any DNA or blueprint to guide it.
Give me the non-biological examples. I want to see this operating system in action.
The classic one is a hurricane.
A hurricane, okay.
Think about it. A hurricane has a distinct structure. The eye, the spiral arms. It moves across the ocean with a purpose, it seems. It grows. It persists for days or even weeks.
And it has a metabolism? It consumes heat from the warm ocean water to power itself?
Exactly. It eats heat, it moves, it has a structure, and it dies when it starves over land.
But it has no blueprint. There is no hurricane DNA telling it how to spin.
None. It emerges spontaneously because of the physics of heat, moisture, and the rotation of the Earth. It organizes itself.
What about sand dunes?
Sand dunes are another great one. The wind is random. The sand drains are random. But physics forces them into these perfect rhythmic waves that can march across a desert.
Or a snowflake.
A snowflake. Incredible, intricate geometry. No designer. Just water molecules freezing according to physical laws. Or look bigger spiral galaxies. Trillions of stars organizing themselves into beautiful arms.
So organization isn't special to life at all?
No. Biology didn't invent organization. Biology just refined it. It hijacked it. Life is basically self-organization on steroids.
Yeah.
It took these natural physical tendency, the tendency for matter to form patterns, and found a way to record the instructions, to lock them in.
Okay, so I'm with you on the physics.
Yeah.
Matter wants to organize, energy flows through us, but there's still a massive gap between a hurricane and a human.
Of course.
A hurricane doesn't remember anything, it doesn't learn. Most importantly, it doesn't evolve over generations. How do we cross the bridge from cool whirlpool to actual living cell?
This is where we have to leave pure physics and enter the realm of chemistry. We have to talk about the hardware. If you want to build a life form, you can't just use any atoms you find lying around. You need very specific building blocks.
And the hero of this part of the story is carbon.
Carbon is the absolute king of the periodic table. You hear carbon-based life forms in science fiction all the time. But the reason isn't random. It's all about geometry.
Explain the geometry. Why is carbon so special? Why not iron or helium?
It's about its valence electrons. Carbon has 4 electrons in its outer shell that it wants to share. That means it can form 4 stable bonds with other atoms.
Okay.
And it can do it in a Goldilocks way. The bonds aren't too tight, so they can be broken and reformed, but they aren't too loose, so they don't just fall apart. It's just Right.
It's the ultimate Lego brick.
It is the ultimate Lego brick. You can snap carbon atoms together to form long chains. You can make rings. You can make sheets. You can build incredibly complex three-dimensional shapes like proteins and DNA. No other element offers that kind of flexibility.
What about silicon? Sci-fi always loves silicon-based aliens. Silicon is right below carbon on the periodic table. It also has 4 electrons.
It does. It's the obvious runner-up. But silicon is a bit clunky. The bonds it forms are weaker. It's much harder to build long, stable chains. And there is a fatal flaw with silicon metabolism that makes it really unlikely for life as we know it.
Which is?
The waste product. When we burn carbon for energy, what do we make?
Carbon dioxide.
CO2.
Which is a gas. We just exhale it. It's easy to get rid of. Now, when you burn silicon, you make silicon dioxide.
It is sand.
It's solid quartz. Imagine if every time you exhaled, you had to cough up a mouthful of sand.
Yeah, that's going to make breathing a little difficult.
Exactly. So, purely from a chemical standpoint, carbon is really the only game in town for building complex, flowing, dynamic life.
Okay, so we have the bricks. Carbon. But we need a builder. We know that chemical reactions in a test tube can take thousands of years. But life happens in milliseconds. How do we speed it up? You need catalysis. A catalyst is a substance that fast-forwards a chemical reaction without being used up itself. In our bodies, we have a special name for them.
Enzymes.
Enzymes. They are the biological catalysts.
They're the workers on the construction site.
They're the construction crew. They grab 2 molecules, orient them perfectly, smash them together, and then move on to the next pair. They make reactions happen millions, even billions of times faster than they would by chance.
With it all, then we'd be dead.
Without enzymes, your metabolism would grind to a halt and you'd die in seconds.
But here's the chicken and egg problem. Enzymes are these incredibly complex proteins. You need DNA to tell your body how to make the enzymes. But you need the enzymes to read the DNA and build the proteins. How do you start that loop? Who built the first tool if you need a tool to build a tool?
This is one of the biggest questions in the origin of life field. How do you get the motor running? The leading theory right now, the one with the most evidence behind it, is the RNA world hypothesis.
Okay, break that down for me.
So, today, in our cells, we have a strict division of labor. DNA holds the information. It's the library. And proteins do the work. They're the construction crew. They are 2 separate things.
Right.
But RNA is this magical jack-of-all-trades molecule. It's chemically similar to DNA, so it can store genetic codes.
Okay, so it can be the blueprint.
It can be the blueprint, but it can also fold up into complex 3-dimensional shapes, just like a protein can.
So it can also act as a catalyst. It can be the worker.
Yes. We call them ribozymes, RNA enzymes. It turns out RNA can be both the blueprint and the carpenter.
Wow. So in the primordial soup, billions of years ago, you didn't need this complex system with DNA and proteins. You just needed some RNA strands floating around.
That's the theory. Imagine a warm little puddle. You have these RNA molecules floating in it. They are copying themselves, maybe imperfectly. They're splicing each other, acting as a crude, self-replicating chemical system.
Is that life?
That's the million-dollar question, isn't it? It's chemistry that replicates. It's molecular evolution. It's definitely not a rock. But it's not a cell either. It's the bridge. It's the gray area.
But if it's just floating around in a puddle,
Yeah.
wouldn't it all just drift apart? You know, if I have a really great genetic code, a great RNA strand, but it just floats away into the ocean, I'd lose it. It's gone.
Exactly. To evolve, you need to keep your good stuff together. You need a container. You need to define me versus the world. You need compartmentalization.
You need the bubble.
You need the bubble. And again, physics gives us this for free. We didn't need to invent the cell wall. Nature did it for us spontaneously.
Ow.
Lipids, fats. Imagine you have a molecule that looks like a little tadpole. It has a head that loves water and a tail that hates water.
Like soap or oil.
Exactly like soap. Now, if you dump a bunch of these molecules in water, they panic. The tails all want to get away from the water. So they huddle together, tails inward, heads facing out toward the water. And spontaneously, without any instruction, they form a sphere, a little bubble called a vesicle.
So if I just shake up some oil and these water-loving lipids in water, I get instant empty cells.
You get the shell of a cell, a lipid bilayer. It happens automatically. Now, imagine if some of those self-replicating RNA strands from before got trapped inside one of those bubbles by accident.
Ah. Now you have a private laboratory.
Correct. Now the chemicals are concentrated, they bump into each other more often, the reactions speed up, and crucially, if that specific bubble has a good mix of RNA1 that helps the bubble grow or maybe steal lipids from its neighbors, that bubble survives and grows.
And ones with bad RNA don't. Natural selection begins.
The races have started. You have a container, you have a replicating code inside, and you have a rudimentary metabolism. You have a primitive cell, a protocell.
This is incredible because it removes all the magic. You don't need a lightning bolt from the sky. You just need carbon, water, lipids, and a lot of time.
And the laws of thermodynamics driving the whole process.
So if we look at this history, from the rock to the crystal to the RNA soup to the bubble to the first bacteria, we're really seeing a slope, a gradual incline.
A gradient. This is the core argument of our sources. We need to stop asking, is it alive, as a yes-no question. We should be asking, how alive is it?
It's a spectrum of complexity.
Exactly. Think of it like a color gradient. Where does the color red turn into the color orange?
There's no single line. It's just reddish-orange, then it's orangish-red. It's a blur.
Life is the same. Let's try to map out the steps of this gradient based on what we've talked about.
Okay, walk me through the steps, from least alive to most alive.
Okay, step 1, the very bottom. Self-replication. A crystal growing. A fire spreading. Very low complexity, but it copies a pattern.
Okay, step 2.
Evolution. Things that not only replicate, but do so imperfectly, allowing for variation and selection. This is where you get change over time.
Step 3.
Metabolism. You're coupling an energy source to do work. You're creating that whirlpool of order we talked about.
Step 4 would be?
Compartmentalization. The bubble. Defining an individual self that's separate from the environment.
And the final step, the top of the gradient.
Integration. This is when the code, the DNA, fully controls the hardware, the metabolism. When the information and the body are one self-sustaining, self-reading loop.
And this framework completely solves the virus debate.
It does, completely. Under the old binary view, we have to fight. Is the virus alive? Yes or no?
Right.
Under the gradient view, we just say, a virus is at step 2. It has replication and it has evolution. It lacks metabolism and integration. It's, 40% alive.
40% alive. That makes so much more sense. It just occupies a specific niche on the slope of complexity.
And we, humans, dogs, trees, we are just at the high end of that slope. We are solidly at step 5. We aren't a different category of matter. We are just the most complex version of the whirlpool we've found so far.
But there's one more layer to this gradient, isn't there? The sources got really deep on this. It's not just about complex matter, it's about complex information.
Yes. This is where the physics and chemistry start to bleed into philosophy. Life is matter that processes information in a very special way.
The source made a really important distinction between physical information and meaning.
Right. So a rock has information. A physicist could measure its mass, its shape, its velocity, its chemical composition. That's all information.
But the rock doesn't know that. The information doesn't mean anything to the rock itself.
Exactly. But biology is different. Think of a book. Physically, what is it?
It's just paper and ink. A pile of wood pulp with some carbon smudges on it.
That's the physical layer. But if you, a reader, look at it, those ink marks transform into ideas. Love, war, a recipe for chocolate cake. That is interpreted information. It has meaning to the system reading it.
So in biology, who is the reader?
The cell itself. The cell is the user. It reads its own DNA. It doesn't just see a long chemical molecule. It sees an instruction. Build the specific protein. Stop growing now. Divide. The system interprets its own code to maintain its own existence.
So the difference between a rock and a mouse is that the mouse is matter that has learned to read its own instruction manual.
That's a beautiful way to put it, yes. Life is matter that has gained the ability to interpret instructions about itself. And this is what creates the illusion of purpose.
Purpose, yes. We always use that language. The wolf hunts to eat. The bird builds a nest to protect its eggs. It sounds like they have a goal, a future they are aiming for.
We call that teleology. And physics hates teleology. A rock doesn't roll down a hill in order to get to the bottom. It just rolls because of gravity. There is no future goal pulling it forward.
But the wolf does seem to have a goal. Its goal is dinner.
But the source argues that this purpose we see is retrospective, not prospective. The wolf doesn't necessarily have a conscious, future-oriented plan. But for millions of years, the wolves that had the instinct to hunt survived. The wolves that sat around staring at the sky starved to death.
So the behavior exists because it worked in the past, not because the wolf knows it will work in the future.
Exactly. Evolution is a blind editor. It just deletes what doesn't work. The result looks like brilliant, purposeful design, but it's actually just a history of what survived. It's survivorship bias on a grand scale.
But as we climb this gradient of information processing, from the cell reading DNA to the nervous system processing signals to the brain processing thoughts, we hit the final weirdest step.
What is this?
The internal movie. The subjective experience. The fact that I don't just process photons of a certain wavelength, I see the color red. I feel pain.
The hard problem of consciousness. This is the absolute frontier. Physics can explain the wiring, neuroscience can map the neurons firing when you see red, but why does it feel like something to be that system?
Does our organized physics theory hold up here? Can a whirlpool feel?
The prevailing view in the research we looked at is that consciousness is what happens when information integration hits a certain critical threshold of complexity. When the whirlpool gets complex enough, it starts to create a model of itself.
So consciousness isn't a ghost in the machine, it's just what the machine feels like from the inside.
Precisely. It's the user interface of a highly complex, entropy-fighting information processing system that needs to navigate the world. It's what integrated information feels like.
This has been a wild ride. We've gone from rocks to souls, basically. But I want to try and land this plane. What does this all mean for the listener? We've stripped away the magic. We've said there is no spark. We're just eddies in a river of entropy. It feels a little cold, doesn't it? A little mechanical.
I actually think it's the opposite. I find it incredibly warm and connecting.
How so?
Well, if life required a magic spark, some non-physical alien energy, then we would be strangers in this universe. We would be something other, something inserted into the physical world, but not actually of it.
We'd be tourists.
Exactly, tourists. But if life is just organized physics, it means we belong here. We are a natural consequence of the universe's laws. It means that the universe, in a way, wants to create life.
Wants might be too strong a word. You're flirting with teleology again.
Okay, fair point. Let's say the universe is biased toward creating life. The physics is set up in such a way that if you have a flow of energy and the right chemicals, the emergence of complexity like life is almost inevitable. It's what matter does when you leave it alone for long enough.
That has huge implications for finding life elsewhere. For aliens.
Massive. It means life is probably everywhere. The universe should be teeming with it. And it means it doesn't have to look like us. If life is just organized physics, it could be made of silicon and liquid methane. It could be plasma clouds in the atmosphere of a star. As long as it fights entropy and processes information, it's alive by this definition.
It really broadens the definition of who our neighbor might be.
And for us, for human significance. Does being just physics make us less special? I'd argue it makes us more amazing. We are stardust, dead, cold, inanimate stardust that has organized itself over billions of years to the point where it can think. We are the universe asking questions about itself.
We were the part of the universe that woke up. That's a bumper sticker right there.
It really is. It's a beautiful thought.
So let's wrap this up. We started with a broken checklist from a biology textbook. We realized life isn't a thing. It's a process, a whirlpool powered by the relentless flow of energy. We saw how chemistry builds the bridge from dead matter, how bubbles create the individual, and how complexity ramps up step by step on a gradient.
From the second law of thermodynamics to the human mind, a continuous, unbroken line, a blur, not a wall.
And I want to leave the listener with one final, slightly provocative thought that I was chewing on while I was reading these notes.
Go for it.
We talked about this gradient. Rock to crystal to virus to bacteria to human, a gradient of information processing and complexity.
Right.
Well, look at what we are building right now. We are building artificial intelligence. We have massive data centers, metabolisms that are consuming gigawatts of electricity. They are processing information on a scale we can barely comprehend. They're responding to stimuli. They're starting to learn and adapt their own code.
That is the big question hanging over everything.
If life is just a complexity gradient, are our own machines now entering that gradient? At what point does an AI become a silicon life form? Not because it has a soul, but because it meets the physical definition of life we've been discussing.
If you drop the biological bias, the idea that you have to be wet and squishy and carbon-based to be alive, then yes, it's a very real possibility. We might be witnessing the birth of a new branch on the tree of life. Step 6 on the gradient.
Something to mull over next time you ask a chatbot to write an email for you. Are you talking to a clever tool? Or are you interacting with a very simple, newborn silicon whirlpool?
It's getting harder and harder to tell the difference.
So the next time you look at a fire, or a tree, or even your laptop, try to see the underlying physics connecting them all. It's all just energy flowing, trying to find a shape.
We're all just eddies in the same river.
Thanks for listening to this investigation. Stay curious, and we'll catch you on the next one.